Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so it's my great pleasure here to have Jonas Peters from ETH Zurich. So actually, I got to know Jonas in the Max Planck Institute in Tübingen, where we both did our PhDs. Jonas has worked on causality and has worked with the greatest minds working on causality all around the world. So you were working with Martin Wainwright in Berkeley, with Peter Speartz at CMU, and also with our very own Léon Boutou at Microsoft Research. And now you're in Zurich, but I think you soon have your own group working all on causality. So it's very exciting to have Jonas here as an expert on causality, and in particular because he will give us a sort of tutorial on where causality stands, and I hope we all can sort of profit from that insight. So thank you very much for coming here.
Yeah, thanks a lot for the invitation. So it's a great pleasure to be here. It's a very nice building. I didn't know it before. It's a very nice town, so I'm enjoying my stay already. I'm meeting a couple of you afterwards, so I'm looking forward to this. Oops.
Buy some warm beer later.
Yes, exactly. So can you hear me? I guess that should be fine. Okay, so I will give sort of an overview talk, maybe about a few methods at least. It's limited time, and let's see whether I will have time to talk a bit about domain adaptation, which is something that we recently looked at. But most importantly, so please interrupt at any time. So I know that causal inference, especially if I'm not used to it, sort of is a bit a funny way of thinking. And if something is unclear, it's most surely because of you, because of me. So please, please ask me, and I will repeat what I said or try to rephrase it. So it's definitely not because of you. Okay. So this sort of contains a couple of work. So these are the collaborators from ETH. It's Peter Bühlmann, Nikolai Mainshausen from the MPI in Tübingen. It's Dominik and Bernhard. Joris Moy, who's now at the University of Amsterdam, and Shiva and Martin from Berkeley. Okay, so, and here's what I think about causality, and I'm more than happy to discuss if you disagree. So I think we often work with IID samples from some joint distribution P, and my claim is, at least for this talk, that in a lot of situations we are actually interested in a different distribution P tilde. And to give an example, you may have seen this before, but it's sort of my favorite, so that's why I show it again. So what you see here is a study from 2012 where people look at the chocolate consumption in kilogram per person for different countries, and at the same time the number of Nobel Prize winners per 10 million. And here apparently there's a strong correlation. So you might figure out that Sweden is sort of an outlier. This tells you maybe something about the quality of the chocolate between Switzerland and Germany. But in fact, so this is a sample from a joint distribution, and my argument is that although this might be interesting for prediction, so imagine you are a country and you don't know how many Nobel Prize winners you have, you may just measure the chocolate consumption and then you get an idea of how many Nobel Prizes you have won in the last years. But this is a sort of a prediction task. But my statement is that often we are interested in a different distribution P tilde. And what would this be in this example? So here we are interested in sort of the causal relationship between chocolate and Nobel Prize winners. So you can phrase this as saying we are interested in a distribution P tilde where we randomly distribute chocolate. So we take, like, let's say we have a UN meeting and all the presidents from all the countries are coming towards us, and then we randomly tell them, okay, your citizens have to eat that much chocolate every year. So now if you do this, then you may look at the data, and if you still see that there's a correlation in this new distribution P tilde where you have randomized over the chocolate, then this is a sort of quite a different statement, because then it really means, well, eating chocolate helps, right? So this is a way to phrase those sorts of interventional distributions. So saying, well, in fact, we are interested in some P tilde. And then, of course, the next question is, well, how do we relate P and P tilde? So I gave you an example, but it's obvious that if P and P tilde are arbitrarily different, we cannot learn anything about P tilde just by observing P. And so this is my argument. So I would claim that causality is sort of a very useful language in this respect. So causality gives you some tools or some phrases that are very well suited for defining the relationship between P and P tilde. And this I would like to spend a couple of minutes on sort of to make a bit more precise what I mean by this. So the language we are using are structural equation models. So maybe you're familiar with this. If not, it's something very simple. And I define it basically on this slide. So what is a structural equation model? We say that a joint distribution has been generated by a structural equation model with respect to a certain graph. Let's say this one, if the following holds. So if we can always write a random variable as a function of its parents in the graph and some noise variables. So here, x1, for example, in the graph has one parent, namely x3, and the corresponding structural equation says x1 is a function of x3, of its parent, and some noise. x3, on the other hand, doesn't have any parents, so it's just a function of noise. So then we have to make some more assumptions, and we can also discuss them so you can relax them a bit. One is that the noise variables should be independent, and the other one that we are concentrating on now is that the graph doesn't have any cycles, which is a strong assumption in reality, I think. So one observation, and this is not so difficult to see, I think, is that with this definition, so this really gives you some sort of distribution. So if I tell you the structural equations, and by this I mean I also tell you what are these functions and what are the distribution of the noises, then you can generate a distribution with this information. A simple way to see this is, well, you just think about simulation. So you write a program, and what you do is you first simulate from this noise variable, you plug it through this function, and you get samples for x3. So then you take the next variable, let's say this one for x1, you already have the samples for x3, you generate samples from n1, plug it through the function, and you get samples from x1. Right? So this tells you, if you're given a structural equation model, you have a joint distribution. Okay, so the example that we have seen before, and so here I make now the assumption that we know the ground truth, namely that, so this is at least my guess, maybe you have other ideas, the correlation between chocolate consumption and Nobel Prizes probably comes from some economic strength of the country. So in rich countries, people spend more money on chocolate and research. So this is my guess. So this is the example, and now if we assume that we know the distribution P, here's what we can do. So this is our structure. Now we observe some data. So let's say we also have access to this, these economic indicators. Now what we can do is the following. We can compute statements in the new distribution P tilde. So how do we do this? So first of all, I specify what I mean by the distribution P tilde. And so what I am interested in is by a distribution P tilde where I replace this first structural equation. So here I'm saying, well, I'm not interested in sort of the chocolate that is eaten because the country is rich, but I really want to, so you can think of a randomized study here. So I want to break this dependence. So what I do is I replace this structural equation. And I think this is a pretty neat language. So what you say is, start with the distribution P, we consider like a certain structural equation model, and then we are just replacing this structural equation here. And now, this is something that I will not talk a lot about, but now you can do all kinds of inference. So if you observe data, for example, from the distribution P, but in fact, you're interested in the distribution P tilde, but you know the structural equation models. So here, for example, you can try to estimate these functions and the conditionals, if you like. So then you can make all sorts of statements. So then you can ask, okay, is eating chocolate really helpful in getting a Nobel Prize or not? And you can do proper statistics. So if you don't have access to the full distribution P, but only to samples, you can construct confidence intervals and so on. Okay, so this is another example. It's very simplified. That we have been working on at Microsoft Advertisement. So this is another structural equation model for advertisement placement. So again, very simplified, but you may think that a user has some certain attention. So he wants to buy some organic apples or whatever, and then he goes to a search engine like Bing and puts in a query. And you also have some user data, like the location of this person or the time of the year or whatsoever. So then this is the mainline reserve, I should say. So this is a parameter that you may be familiar with. So basically, it tells you how many, or it has an influence on how many ads do we want to show on the mainline. So this is the area above the search results. And then at the end of the day, you have something that you're interested in, namely whether a person clicks or not. Okay, so now you can gather information, so you can gather data from this system, and this is again a distribution P, but again, you might be interested in a different situation, namely in a distribution P tilde, where now what you do is you replace this edge here, so you replace this conditional. And why is this? Because this is something that Bing, for example, has full control about, right? So this is something like the parameter setting. So given the user data, this is a parameter. You can think of a value that takes, or a parameter that takes real values. So this is something that you can change, you can control about. And because you want to make money at the end of the day, or you want to get clicks, you can ask questions like, well, how many clicks would I get if I replace this structural equation? So if I replace my parameter settings by something else. So maybe, yeah, a question.
So when you say we can compute P tilde and then change the structure, then you're really designing an experiment that allows you to figure out what P tilde is? Is that how?
Yes and no, I think. So because here we don't, that's sort of the nice thing about this, is that if we only have data from the distribution P, but we are interested in this new distribution P tilde, we actually don't need data from P tilde to infer something about the system's behavior in this new distribution. So I don't have a blackboard, I guess, but so in principle what you can do is, this is sometimes called inverse probability weighting, for example. So now imagine a specific situation, that's something we looked at, you're interested in the expected number of clicks in the new environment P tilde. So what you could do is, you could take the old samples that you gathered in the distribution P, and now you reweight the samples. Because maybe some of the samples, because of some randomization here, some of the samples look pretty much as if they would be coming from P tilde. And those are the samples that you want to give higher weights to. So in a way, you're using the information that you gathered in the old environment to make a statement in the new environment. But so you are right in the sense that if you want to sort of check this, for example, you should be able to also physically do this, right? Because at the end of the day, maybe you're saying, well, I can propose a new advertisement system that uses a different parameter setting here, and that seems to work much better, and sort of it's nice if the people can really try it, right? So if you say, well, we would get a much higher number of clicks if the users would like to buy more things, then this is sort of maybe a valid statement, but how do you make the users to buy more things? It's sort of, it's a bit vague there. Okay, is this sort of roughly clear? Okay, so now, so I'm again, this is another example, but I don't go into the details here. So I don't tell you precisely what are the best statistical methods to sort of estimate the behavior under the new distribution. But in a way, this is, so what I wanted to stress here is that we are using the causal language to go from P to P tilde, and the rest, if you like, is more standard statistics. Okay, and now there are a couple of questions. So one is, what do you do if there are a lot of hidden variables? And this is, for example, something that you can learn a lot about if you read Judea Pearl's book. So I found this book amazing because no matter how often you have read it, you read it again and you find some new stuff in it. But this also has a bit the problem, it's very difficult to read it when you don't know about causality. So there are lots of things that seem a bit weird. And one reason is that sort of he's dealing a lot with these questions. So can we infer something? And this is the case here. If we don't know anything about the user intention, or if there's another variable that sits up here and influences a lot of other things. So can we still, although there are some hidden variables that we cannot measure, can we still make sort of this causal inference? And this is, if you like, again, I won't talk about this right now, but this is something you can read, for example, in Judea Pearl's book. The next question is, and this is something I would like to address in the rest of the talk, is the following. So what happens if we don't know the graph? Right? So what can we do then? Because as I said, if we are given the sort of the causal knowledge, meaning this structural equation here, so the structure, the graph, and the distribution P, we can use both of these things to infer something about the new distribution P tilde. But what happens if you don't have the structural equation model? And this is something, so where we only have the distribution. And this is something I would sort of maybe briefly tell you a few ideas what you could do then. Sort of the problem clear? Okay, otherwise just interrupt. Yeah.
Which one would be the book to read before the Pearl book? Because I read the Pearl book and I did encounter the difficulty that you were just mentioning. Is there a good book to read before it?
I mean, maybe other people say different things, but I think there's none. So I'm giving I'm giving a lecture at the moment at the ETH, or I'm starting to give a lecture. So I'm preparing a script, and I mean, it also depends a bit on your background, right? But if you're coming, so I studied statistics and machine learning, and if this is your background, I think there's no good book at the moment, yeah. But we are working on it. So let's see. I mean, we are trying.
So, but if you are coming from a different background, then what would be a good book?
What would be the background?
What would be the background and the book? Okay, so maybe put it this way. There are the Judea Pearl book is sort of, it's specializing on the question, what happens if I know the graph? Okay, and then he's answering, as I said, what happens with hidden variables. There's another book from the CMU people, so Peter Spertus, Clark Lima, Richard Shines. So what they are addressing on is, so they have the constraint-based methods that I will also briefly mention in the talk later, and they have sort of this focus, they focus a lot on independencies and conditional independencies. And then you have another book that comes from, or some other books actually that come more from a statistical point of view, where you may have heard about the potential outcomes. So this is a slightly different language, and this is also a bit a problem that people inside causality are fighting a lot about which language to use. Whereas it would be nice if they just say, well, this language is very well suited for these kinds of problems and these for these kinds, but they're not. So they're really fighting which language to use. And this is quite a different sort of group of people working on it. And in UK, for example, if you go to a UK causal inference meeting, there you have a lot of people that work with instrumental variables. And this is something, probably I won't have time for this. I also have a few comments on at the last slides. This is something that also comes from really like a practical application. So where people have medical studies, they have like treatments where you have like different phases, and you have to consider what happens if people figured out that they take a placebo, and then stop taking it. So how do you deal with this? So in a way, you have these people that are quite different, I think. But it would be nice to sort of merge these a bit more. Okay, so for the rest of the talk, I would like to present you 3 ideas that have a different flavor of how you could try to learn the structure of the graph. And the first one is something, we were a bit surprised, so this got actually picked up by Slashdot. I'm not sure whether this is a good idea or not, so the comments are a bit funny to read. But so now I will tell you about this revolutionary new statistical test. It's actually not so much revolutionary, it's very simple, and it's based on the following idea. So again, I told you about these structural equation models. This is yet another graph, the same story as before, but the problem we are trying to solve is the following. So assume we are given access to a distribution that has been generated by this structural equation model. Now the question is, can we somewhat infer, sorry for the abbreviation here, DAG means directed acyclic graph. Can we somewhat infer the structure of this graph from the joint distribution? It would be nice, of course, if we can infer like all functions and all noise variables and so on, like the distribution of the noise variables. But now let's sort of make it a bit easier at least and say, can we infer the structure of the graph? And the answer is no. And so I won't prove this here, but intuitively, the reason is that this model class is extremely general. So imagine that you have a fully connected graph, so with a lot of edges. Then sort of these functional models, they are extremely general. So also imagine now, another way to look at this, imagine we know that x4 has 2 parents, namely x2 and x3. And we know that x4 is a function of x2, x3, and some noise. Now try to fit this model. So is it possible to find this function f4? And then it will be very difficult. So this is also another way to look at it, why this model class is so incredibly rich. Okay, so this sort of is a bad result. It's sort of negative. The question is whether it's hopeless. And so here's something that we looked at in the last years for quite some while, because it turns out if you reduce the complexity of the model class, so if you make the assumption that the noise acts in an additive way, rather than the function acts jointly on the variable and the noise, then it turns out that the answer is positive. So as long, it's maybe stated a bit different here, but as long as you're not in the linear Gaussian case, so if you have Gaussian distributions, and now the statement is, as long as the functions are not all linear, then you can identify the structure. So this is what's written here. So if we assume that everything is Gaussian distributed, then the statement is, the DAG can be recovered from the joint distribution as long as the function is not linear. And also, I mean, I don't state this here, but this is something that's known under the name lingam. So you also have the statement, if the function is linear, then the Gaussian distribution is the worst case. So this means, in a way, the linear Gaussian case is not identifiable, but the rest is. This is sort of a bit funny because the general, so you saw that the very general model is not identifiable and the very specific model is not identifiable, but a lot of things in between are. Okay, so again, because of lack of time, I won't go into like the intuition why this is the case, but I'm happy to discuss this afterwards as well. Okay, and now what we did is the following. So in a way, in the causal inference domain, I found that what's also a bit problematic is that if you look at real data and you try to estimate a graph structure, then in many situations you just get an output, and in most cases you can somewhat reason that this is a very good output. Because if you look at variables like, I don't know, income and height and education, then I think a lot of results would sort of look very good. So what we tried to do is we collected data sets where we know the ground truth. So these are now, I think, something like 88 data pairs of random variables where we know which of the variable is the cause and which is the effect. So this is a specific case because we only have 2 random variables. But we would be very interested in looking at higher dimensional data sets as well. And so now I know that it's sort of causal inference is a bit maybe a voodoo part of machine learning. And some people would say, well, how is it possible to infer something about the causal structure from just observational data? And so for those people, I always like to show this scatter plot here. This is 41. So I won't tell you which one is the cause and which one the effect, right? But if I would ask, so maybe we can do the test. So who of you thinks, so let's call this variable y and this variable x. So who of you thinks that x is the cause of y? Who thinks that y is the cause of x? Okay, so we have a few.
Like bimodal
Say,
distribution. Just go ahead.
okay, because of democracy, we have persuaded that x, or we have decided that x is the cause. So, I mean, you're right in a sense that it could be bimodal. But, okay, so first of all, the truth is that x is really the cause and y is the effect. So I think x is the day of the year and y is the temperature. And so one reasoning would be that sort of it could be the other way around, but somewhat this model would look very, very weird because you have very like small support for these y values, and then suddenly it becomes bimodal, as you said correctly. And maybe there are some examples like this, but somewhat the other model seems to be much more natural to us. Okay, anyhow.
Could you go back to the previous slide? So when you say you can reconstruct the structure, does this mean assuming only 4 nodes?
No. This is general. This is.
So you would also be able to rule out another hidden cause for 2 of these nodes.
So we have been working on this, but it's not included in the slide. So in this slide, we assume everything is observed. So the reasoning is, so the precise statement is, if the distribution is generated by this model with a certain graph, it cannot be generated by a different model with a different graph. And now, if you have a hidden variable, that's the intuition, you will not be able to find any model that fits the data. So you do a model check, and in this way, you could at least, so this is the first step, you could say, well, something is fishy here. Maybe there's a hidden variable, or maybe there's a model misspecification, but at least you can say, well, I don't know for sure. And then the next step is try to fit a model including a hidden variable, and this is a bit more difficult.
Okay, but you would be able to say that
we will be able to say no at the moment, yeah. Or we will be able to say I do not know, yeah. Okay, so this is sort of we try to include this as a benchmark data set, and all I want to show here is that this is not a proof that causal inference works, but I think the results are sort of promising. So what we should be looking at is this additive noise. This is the red curve, and what you see here on the y-axis is the number of correct decisions. And thanks for the question. So because in some situations you don't want to make a decision because you think maybe there's a confounder or none of those models fits very well. So that's why we included the x-axis as well. So what does it mean? So here 100% means you always have to decide on all data sets. And if you go further to the left, it means you can make less decisions. And as you see, this is also encouraging, I would say. It's not a proof for anything, but it's encouraging that the examples where you're pretty certain about are also more correct. Which would indicate that if you are lucky and the nature really generates data in this way, you have to be lucky because it's a model assumption. But if you are lucky, then your decisions seem to be more often correct than incorrect.
So different lines are
different methods. Yeah, I mean
methods for detecting.
Yes,
okay.
yeah. I think I'll skip this. We can discuss them later.
And the ground truth is a question of judgment, yeah?
Yes, so we use things like, so we are also happy, I mean, we published this data set and we are happy to receive comments on this. What we usually did is, I'm not saying this is perfect, but this is the best we could come up with. We were, I think, 6 people collecting data sets, and we always chose the one where all of us 6 people agreed before seeing the data. So one found the data set, sent around the variables, and then if all of us agreed on which is the cause, then we put this in. These are variables like very different kinds. So, okay, you have seen day of the year temperature. There's something like availability of clean drinking water and baby mortality rate. There's some financial things, some physical things like sunspots. So there, we try to include.
So it's often easy to say which one, if these are only 2 variables, then which one is likely to cause the other. But ruling out confounders is almost impossible.
Yes, I agree. I mean, so there we hope that the confounding is not too strong. But at least then you would say, well, at least this partial knowledge about the ground truth, which is the cause and which the effect, at least this is correct. And maybe as a side note, so I mean, again, this might vary if you ask different people working in causality. But what I believe in is not that you use causality as sort of a black box. You look at some observational data and you get a ground truth with 6,000 nodes of biological, let's say, genes, and you get the correct graph. So what I believe what causality could do is that it gives hints to the experimentalists. So the biologist analyzes some data, or I mean, we discussed this earlier, you have some advertisement system or something where you observe some data, and then maybe the causal inference can tell you, well, this looks like an interesting variable, maybe you should try to intervene on this one. Because in biology, for example, you cannot, I mean, it's very expensive, you cannot do all the experiments. And if you have this point of view, then maybe it's also not that bad if there's a confounding factor, because what matters is really the direction of the edge in this case. Because then you would say, well, if you really try, and in these cases, and try to intervene on the node that sort of the causal inference person suggested, then you will see a response in your experiments. As a side note, maybe.
Sorry about the data sets. Did you include things like the chocolate Nobel Prize example where
No.
there isn't a clear direction?
No.
And did you reason about the number of hiddens associated with each sort of relationship?
No.
Like you guess, because you could sort of categorize saying, okay, yeah, this is a very deterministic relationship. I believe that there is no other hiddens involved in this relationship, while in others there might be a number of other hiddens involved in that relationship.
We don't make a distinction. So usually when we know that there's a strong confounding and a lot of hidden variables, so even if the chocolate has some effect on your thinking ability, this will be a tiny effect to the huge effect of the confounder. So this is when we say the confounding is way too much, we don't include this. So, but it would be interesting to have categorized examples like this.
So there's a limit to the resolution that you can detect in some sense.
Okay, so now, I mean, what you can do in simulations, this is easy. Theoretically, to analyze this is much harder, so we are working on this right now. is the question about model misspecification. So what happens if you have an additive noise model and now you're perturbing this with a confounder? So in simulations, it's not surprising. So what you see is at the beginning, you still find the correct direction. And if the confounding is too strong, you say, I do not know, because it's a model misspecification. And analyzing this, I think, is pretty important from a statistical point of view. But I also found it very difficult to find it.
There could be some data sets which just conform to physical laws, right? Like acceleration, velocity, and...
We also have some of them included.
Okay, so but do you have you marked them, saying, okay, these are sort of very, very clear where there is no other confounding?
Maybe not. Maybe we should, yeah. So I think in general, no, we didn't make a distinction. So I think the general rule was there's very small confounding included, but we should, I think that's a good comment, yeah. Okay? So this is sort of the first idea that says, well, if you make structural assumptions, then you are able to gain in terms of identifiability. And now comes the second one. This is a more classic one, but I think it should not be missing. It should at least be mentioned. This is something that we call now independence-based methods. Some other people call it constraint-based methods. So this is the work by, for example, the PC algorithm, which stands for Peters, Burtis, and Clark-Limmer. Those are the people who invented them. And the idea is as follows. So you may be familiar with the usual graphical model stuff. So if you look at a graphical model, so it sort of doesn't, you see that it's a slightly different flavor because you don't need the language of structural equation models here. So if you just look at the graphical model, what it does, it encodes some independencies, right? So here, for example, you see that the distribution is Markov with respect to this graph. This is what we usually assume. And this implies that the variables x1 and x2 are independent. And you have conditional independencies. For example, x1 and x4 are conditionally independent given x3. But you also have some funny ones. So for example, x1 and x2 are dependent if we condition on x4, right? So now what you do is the Markov condition sort of gives you one direction. It tells you, if you're familiar with d-separation, so if you have a d-separation in the graph, you have an independent statement in the distribution. And now the trick is very easy. All what you need to do is you need to assume that it also holds in the other direction. So, and this is what we call faithfulness. So you assume that as soon as you have an independent statement, you have the corresponding d-separation statement in the graph. And if you make these two assumptions, so they are really the reverse of each other, then you have a one-to-one correspondence between d-separation statements, which are just graphical statements of the graph, and conditional independencies in the joint distribution. And now what do you do? You're given the joint distribution, so what you do is you choose your favorite independence test, check for all conditional independencies and independencies, and then you scratch your head a bit and look for the graph that satisfies all of these conditional independencies. A couple of problems. So one is, and I indicate this here, so this is not unique. And you can think of a Markov chain, for example, x causing y causing z. You will not be able to distinguish this from z causing y causing x. So this is one problem, and this is why I wrote like different graphs here. So this is called a Markov equivalence class. But the principle works as follows. So here, as I said, find all conditional independencies, and then we select the graphs that correspond to these independencies. And you're all computer scientists, or at least familiar with this. Of course, this is not feasible, so you try to be smart about this. And this is really I think in this respect, the PC algorithm is quite genius, because it sort of does this checking of independence tests in a very smart way. Maybe a few comments. So if you try this on simulated data, it does not work very well. And so there are a couple of reasons. One is, of course, these are very difficult problems, conditional independence testing. I mean, here you only have to test given one other variable, but so if you condition on 5 variables in non-parametric independence tests, we have been working on this a bit. I think it's pretty much hopeless unless you make a very strong regularization. And the other one is you also, because you make all these statements, if you make a mistake at the beginning, you are more or less lost. This is also a bit problematic.
You're lost because you're trying to be smart about it. Right?
Yes, yeah.
Because you build on the previous...
Exactly, yeah. Thanks.
Okay. But besides this, isn't this multiple graphs just the corollary of the difference between independence and causation, right? Well, the different graphs would imply different causal models that all agree on the independence model.
Yes, yeah.
So
I agree. But
there's
so
no jump here from independence to causation. There's no way to bridge the gap here.
partly. Because, so in this sense, for example, I mean, I didn't write down the graphs, but I think, so here, for example, this is what we call a V structure. So if you look at the combination x3, x4, x2, so this is a V structure because both arrows are pointing downwards. And this is something you can identify. And the reason is quite, so forget about x1, so assume that this is not existent. So then you find the independence x2 is independent of x3, but if you condition on x4, suddenly they become dependent. And this structure is the only one that satisfies these independence statements. So in general, I would agree. So there's no jump from independencies in general, from independencies to causal statements. But if you really believe in faithfulness, this is another issue. So then in some situations, you can do this. And I mean, this is very involved now, but people analyze now because if you want to do something like consistency or uniform consistency, you have to say that you are not even close to faithfulness. And people analyzed this and said, well, okay, this is a pretty strong assumption. So faithfulness is maybe a reasonable assumption, but what they call strong faithfulness, saying that we are not even close to non-faithfulness, this becomes a very strong assumption. But this may be a bit involved. Okay, but this is sort of another idea that you can do. So you're saying, well, we know that we have this correspondence between the independencies and the graph structure, and now we are a bit sort of clever about this and assume that there's really a one-to-one correspondence, and then we can try to exploit this. And this is also what people try to do. Okay, so if you're happy with this, I would like to spend maybe the last 10 minutes or so on something that we recently looked at, because I thought, so I find this, or I could imagine that this is also interesting for machine learning in general. Okay, but are there any more questions about this part? Good. So then we come to the third idea. So what is this? And now I come back to what I said before about this, that sort of if we are given the structural equation model, we can sort of generate new distributions p tilde by exchanging structural equations. And now we will turn this a bit around. So first of all, we set a slightly different problem, can be generalized, but we are interested, we have a target variable. So you can think of a prediction task, for example. So this target variable we call y. And now we are interested in whether we could somehow find the causal predictors of x1, or causal predictors of y. In this case, it's x1. So now we will do the following. So we will actually assume, not like this is now different than before. We don't assume we have IID observations from one distribution, but we assume that we gather data from different environments. And now the idea is based on the following observation. And in a way, it's trivial, but we will make use of this. So if you change some of these structural equations, but you leave this one as it is, so you do not exchange the second structural equation, the one of your target variable, then what happens is that this conditional p of y given the parents of y, this is always the same. Okay, so some examples. So this is something we have seen before. It's called a randomized experiment. So we randomize x1. So in a way, we are intervening on x1. This could be one of those environments. And if you look at this for a while, you see, well, this didn't change the conditional distribution of y given its parents. It's sort of also, in a way, trivial because the conditional is specified by this structural equation, right? We can like have all sorts of different environments. So here we are changing the structural equation for x4, or you can also change like a couple of structural equations. The idea is even a bit more general, so you can also introduce, I don't know, cycles or hidden variables. You can change quite a bit, but for now we assume that you do not change this conditional here. Okay, and now the overall idea is, if you are like in a multitask setting maybe, if you observe data in different environments, we will actually use this variation of the data for identifiability. So it's really a kind of different idea than what we have seen before. Okay, so how does it work formally? So I will concentrate on the examples maybe, but just to make clear what the problem here is. So we have a target y and some covariance x. And now we observe this in different environments. So we always have like different distributions, and let's say E is the index for the environment. And then our assumption is that we have this, what we call an invariant prediction. So this conditional y given its causal parents. And so here we write this as we have a linear model that holds in all environments. So in all environments, we have that y is a linear function of x plus some noise variable. And here, as you see, the noise variable doesn't have an index, and the coefficient doesn't have an index. So this is really the same in all environments. Just as a side, so this doesn't have to be a linear model. You can, if you like, you can use a kernel machine here, or you can use a deep neural network, whatever you like. All what you need is that this model is always the same in all environments. Okay, and then maybe this is the last difficult concept. So we look now at different sorts of predictors. Okay, so a set S is now a subset of predictors, and we say that it's a good subset if we really get some invariant prediction. Okay, and then the last concept that we need is we look at all those sort of candidate sets of predictors, and we say if there are some variables that appear really in all of those good candidate sets S, these are sort of the interesting variables. So if you see that some of the variables you really need to get invariant prediction, then you say, well, this is a very good variable. Okay, and so this is the thing that we are after. So this is, I will show you now a few examples at least. This is all in the population setting, so we can discuss the finite samples offline. I think I won't have time. Okay, so this is an example. I don't know whether it's a good one. So here we have whether we eat chocolate or not. This is how good the weather is, and the target is whether we are in a good mood or not. And then this may depend, or this may influence whether we sleep well in the evening or not. It's a stupid example, I think. So now the target, so what are the causal parents? So this is x1 and x2. Okay, so this is what we are after. This is sort of the good set S star. Now, if you have only one environment, so if you have only like observational data, this is something I say the sentence. Let's see whether it's understandable. So then we cannot say anything. So then the problem is we always get invariant prediction. So even if you now regress y on nothing, on the empty set, which seems like a stupid thing to do, but even if you do this, you get invariant prediction because you have the same model in all environments, which is just one environment, right? So then, well, if the empty set is a good set, then you don't say anything. But now it becomes better. So now I'm actually changing the environment. I'm also going to a happy place where I can eat much more chocolate. Maybe it's cheaper or whatever. So what happens now is that if you want to find a model that holds in all environments, then you really have to include x1 as a predictor. Because in this environment where I eat much more chocolate, I'm also, on average, I'm happier. So this means if I try to explain the mood by nothing, this sort of doesn't work because it's not an invariant model, because here I will get like different residuals than I would get here. So this means, in short, so you really need this variable x1 to get invariant prediction, and this means that we call this an identifiable causal variable. And now maybe you can already get a glimpse of this. I skip this. So this is what I would like to say here. If we see more environments, this always helps. This is sort of nice. So if you get data from more and more environments, more variables become identifiable. This is the third one. And some other statements that are quite easy to prove is, for example, this one. If you have only one environment, you cannot do anything. So then you do not output anything. And this one, the top one, I'm now doing it the other way around. So this is my favorite one. So you can prove that whenever you are outputting something, so all the variables in the set, they are correct. And this is sort of, I think, what is nice about this method. So in a way, you are only outputting something if you're pretty sure that this is a causal variable. So you are guaranteed that this is like a subset of the true set. And now what happens is that the more environments you see, so the more variation you actually see in your data, the better this is for causal identification. Okay, and so I'll skip a few slides now. Maybe as a side note, this is all population case, but because we are in statistics, the finite sample case sort of, it's trivial, because what we can do is we just do the statistical hypothesis test. And then you get statements of this form, so that says, if you have finitely many data, you still are correct with a very large probability. Okay, this is probably not possible, so I skip this simulations. So what we did, again, maybe only I mentioned the data set that we looked at. So again, we were wondering whether there's some data where you have some sort of ground truth, but it's not like this toy data set that we collected before, because in a way, you already know that sort of the day of the year is causing the temperature and not vice versa. So what we found is this data set, it's a biological data set where you have a lot of genes, so it's a high-dimensional data set. The number of dimensions is much larger than the number of samples. You have some observational data, and so now this is what we treat as a different regime. We also have interventional data, so where the biologists deleted some genes, so they always had targets. And what is nice about this, you get some ground truth. Why? Because it looks as follows. So this is the activity of gene of this number, and this is the activity of this gene. And the blue dots, very hard to see probably from the back, this is the observational data. So this is what the genes usually do. So there's some small correlation that you cannot see here, but this is what's usually doing. Now, if you knock down, or if you actually delete this gene number 5954, what happens? The activity goes down. This is good. This tells you the biologist did something reasonable. But at the same time, you see that the activity of the gene 4710 also dropped down. And this tells you that there's really a causal relationship. So you have, because of these experiments, you have some knowledge about the ground truth. And this is what we looked at. So I found, we spent quite a while on this. A lot of things to learn in these real data sets. I found the results quite promising. I think it's a difficult data set. And sort of our method proposed a lot of correct hits, actually. Okay, but let me sum up. The time is over, I think. So what I tried to show in the beginning are these three ideas for causal inference. So the first one, this was this additive noise. So we're making structural assumptions to gain identifiability. The second one, these are the independence-based methods. So there you're trying to connect the graphical structure with the independent structure. And the third one that was way too quick was this invariant prediction. So there you gain identifiability by observing your system in very different environments. And what is this I would really like to stress again. What is nice is you can control the family-wise error rate. So in a way, even if the biologist tells you these are two different data sets and they're the same, even then you will not make a mistake. So in a way, this is a quite robust method, I think. Lots of open questions. So this is like the idea number 3 was focusing on the target variable. We could extend this to graphs. Combining these ideas would be nice, I think. Nonlinear models, I mentioned this. This will be fine. Okay, this is an instrumental variable setting that I think is nice. Domain adaptation, I didn't spend a lot of time on it. But I think sort of maybe you feel that there should be a relation, because you're sort of the causal language gives you a way to connect all these different environments, and we are looking at this at the moment. And then instrumental variables is something that's very relevant in practice. It has sort of a similar flavor, because here the instrument variable sort of tells you in which regime I'm in. So in case you have seen this model before. Okay, with this I would like to thank you for your attention.
So we have time for questions.
Coming back to the question of how diverse the data needs to be that you observe so that you can make any inferences about the causal structure at all. How is that related to the question of different environments that you mentioned towards the end? And how different do those environments have to be to qualify as different environments? Could you comment on that?
Yeah, I think it's a very good point. So this is what I didn't talk about this, but this is what I meant by finite sample guarantees. Because now sort of one answer would be the method does not care. Because if the environments are not very different, you're conservative, so you're saying, I do not know anything. So then you can say, well, just take the data and look how different the environments are, right? But then what is sort of nice about this I do not know answer is that there are two reasons for this. So one is maybe the environments are too similar. And the second one is maybe we have only seen too few data to actually realize that there are differences, but these differences may be small, right? So this is, for the method, it does not care. It sort of combines those two methods of like not being sure, the sources of not being sure together. But it would be nice to understand this theoretically. So saying, if the environments are that different, how many samples do I need to actually use this kind of difference? And this, we don't know yet. So we sort of we are on the safe side, on the conservative side, right? But this we do not fully understand, I think.
Yeah, so what if we want to get our hands dirty with causality, like trying it out for ourselves? Is there some, like for example, for graphical models, there are like toolkits very early on, like bugs or something, where people could sort of start hacking and get an intuition and working with these things? Is there like a standard causality toolbox or like a toolkit where...
I'm not sure whether you like the answer, but there is, but in R. So the thing is, so there are some versions, for example, of the PC algorithm, and so I remember when I was a PhD student, I downloaded 3 of them, and all of them had different bugs that were extremely hard to find. So, I mean, there's like the group that I'm working on now in ETH, the statistics group, they have some senior scientists, and sort of they have permanent positions, and one of them said that it would be nice to maintain this a causality toolbox. And therefore, this is called PC Alg. And so they are trying to include a lot of C code, but the interfaces and so on, this is all written in R. But I think this is, so they are maintaining this, they're putting a lot of effort into it. So I think the stuff you're finding there is correct, and the name is misleading. So we also included a lot of other methods, so it's not only the PC algorithm, but the package started with this, so that's why it's called PC Alg. So this is something that is becoming, at least in statistics, more and more popular. Because also you need a lot of like graphical tools for D-separations and so on. This is all included. Yeah.
Another question, like it seems that all this existing research has a sort of classical statistical flavor to it, like worst case events are bounded in probability or whatever over some assumptions. But is there a lot sort of also work in trying to pose this as a Bayesian problem, so have an uncertainty on the causal structure and then doing inference over possible causal explanations, causal models itself? Like.
Okay, so this exists. I mean, David Heckerman, for example, he was like, there's also a nice paper, I think, by Daphne Koller that is phrased being Bayesian about Bayesian networks or something. So, I mean, this work exists. The question is, so it's a bit bizarre, I think. So because what they did is, so what they're usually doing is, they're saying, okay, from an independence-based point of view, we cannot distinguish between certain graphs. So now they have a score-based methods, like a likelihood or posterior approach. So what they are sort of doing is, they are putting a parameter on the, like a prior on the parameters that leads to non-identifiability in these independence classes that you cannot distinguish, in these Markov equivalence classes. I'm not sure whether this makes sense. So somehow, I think there was always this frequentist way of thinking, saying, well, we cannot distinguish between these 2 graphs, so we somewhat set our priors such that we cannot distinguish them anymore afterwards. And so David Mackay was one of the earlier people who has said, I think, well, this is stupid, right? We should make use of the fact that if we use reasonable priors in the parameter space, maybe we can use this to actually identify which of the ones is the more likely graph. But I guess people were a bit cautious about this because they said, well, where should this knowledge come from? But I think you can do this. And a few people are trying to do this. For me, it's already difficult enough in the frequentist space, but I think one should be doing this. Yeah. Regarding the first question, if I may add something, because so for me, this is actually quite interesting for me to see, like also some statistics people working on it, and then machine learners. Because as a statistician, I totally agree. So you have this family-wise error rate that they're quite happy about, but then in a machine learning, and so. I have a very good PhD student who's now starting to work on this. From a machine learning point of view, maybe this is not what you want to do, right? Because maybe if you want to do transfer learning, you do not care about only the causal predictors, but maybe you want to get rid of the predictors that you really don't want to use. So this is something, sort of maybe a different flavor of looking at the problem, and I think both views are actually very well sort of justified.
I remember that Bernard made a point at some point where he related causality with semi-supervised learning and talked about the causal direction of predictors. Are you familiar with that?
Yes, so this is a very neat idea, I think. So So something that I didn't talk about and that also leads to identifiability is the following idea. And again, it's an assumption. But the assumption says that, think of two variables, that somewhat the mechanism, and I'm now very vague about the terms I'm using, so you have to look at concrete examples to make this well defined. Somewhat, let's say x is the cause and y is the mechanism. Y is the effect, sorry. So then you're saying the mechanism, so this thing that turns x into y, the cause into the effect, this should be independent of the cause. So somehow this mechanism should be independent of like the distribution of the cause. And the reasoning is that sort of if you get like lung cancer from smoking, somehow there is an internal mechanism. This should be the same in all different people, right? So why should it depend on the distribution of smokers or something? So we have seen, like, if you like these additive noise models, maybe it's debatable, but they may be an instance of this. Why? What is the cause? Is just the distribution of x, and the mechanism is sort of, you can think of this as being the noise. And we assume that the noise is independent, statistically independent from the input. Okay, and now, so this is sort of...
The function class is, so to speak, you have the function class together with the noise is the mechanism.
Yes, and yes. So in a way, we fix the function class. It's a bit vague now, but you can also, if you like, you can also consider the function. And you could say, and there are some methods based on this, if the function sort of coincides a lot, so let's say the areas where the function has sort of a low derivative or something, if this corresponds by chance with the input of having like a low density region or something, then you say, well, this is a bit funny. Where does this come from? So this is an assumption, right? So we are saying the mechanism should be independent of the input. And now, so what is the relation to semi-supervised learning? I think it's pretty neat. This means the following. So in semi-supervised learning, we are interested in the conditional y given x, right? So we are trying to predict y from x. In semi-supervised learning, we have a lot of unlabeled data, meaning only data from x, that we are sort of using for improving the estimation of the conditional. Well, now if you believe the assumption I stated before, means the following. So if x is the cause, and we said that sort of the cause should be independent of the mechanism, this means that no matter how much you learn about the cause, about the distribution of the input, this will not tell you anything about the mechanism, because we assume that they are independent, whatever this means, right? So then this means that semi-supervised learning can never work if you're trying to do it in the causal direction. It can only work if you're trying to do this in the anti-causal direction, which in practice I think happens a lot. So if you think about, I don't know, image classification or something, you want to know whether there's a lion in the picture or not, then usually what you have are pictures. This is the x, and you have the fact, the label is whether there's a lion or not, and the label here is the cause of the picture, right? So often you do this in the anti-causal direction. And so this is something that we looked at. So we looked at all the surveys about semi-supervised learning, and we checked the cases where it was working. And we didn't find a single setting where semi-supervised learning was working in the causal direction. So, I mean, I'm not sure whether this proves anything, but I think that this sort of way of thinking can help also in other areas of machine learning. It's sort of it gives you some other insight that is in a way orthogonal to what people are used to think. This is why I found this neat. Yeah.
Okay, great.
Sorry for running over time. Yeah.
No, you didn't.
So, okay, I did.
Thanks a lot. And yeah, many of you have a one-on-one meeting. Afterwards, we will go to the pub this evening. So if you want to join, just drop me an email or so. So thanks, Jonas, again.